Good evening, everyone. My name is Shubham Rai, and I am a PhD research scholar in Department of Applied Mechanics, IIT Delhi. So today we will be recapitulating week 8 lectures, and then we will focus on some problems related to week 8 lectures. So what did you study in week 8? Let me write it down. Straight up. Okay. So in week 8, you would have studied related to extension, torsion, inflation in a hollow cylinder. Okay. So let me just write. This is week 8. So you would have studied extension, torsion, and inflation in a hollow cylinder. In the lectures, you would have studied firstly related to thick cylinders. So firstly, the derivation was all the derivations were done for thick cylinders, and then sir had focused on applications of thin cylinder also. So when your thickness of the cylinder is very small compared to length of the cylinder, so those kind of cylinders or the radius of the cylinder. So those kind of cylinders are known as thin cylinders. So when thickness is very small compared to radius, so those are thin cylinders. So in real life, they have a lot of applications. Okay. So we will be recapitulating firstly the formulas. I'm not going to derive any of the formulas here, but I just writing down, just write down those formulas. And if you do not remember the derivation, you can again go back to lectures and watch the derivation and clarify your concepts. So here I'll only be writing the formulas, and then based on those formulas, we will do some questions. Okay. So this live interactive session is all about showing you the application part of what you have done in the lectures. Application in the sense, this live interactive solving numerical problems. Okay. Let me write the second topic that you would have studied. So then you would have studied about solving governing equations based on extension, torsion, and inflation of the cylinder. And inflation of the cylinder. Now, and then you would have studied related to solving problems involving torsion of shafts. So, solving problems involving torsion of shafts. Okay. So let me recapitulate the concepts that you would have studied in the lectures. First concept is you would have studied related to twist. What is twist? So it is rate of change of angle of cross section. So we can say that it is rate of change of angle of cross section. Now, rate of change of angle of cross section with respect to length of the cylinder. Okay. Or if you are talking about a rod, so with respect to length of a rod, or length of a shaft. So it is not with respect to time here. Okay. So if I write down the formula, so twist is written as total change in angle to the total length. So this is twist. And obviously here, whatever derivations have been done in this course, in these lectures, so these derivations are based on small deformation theory. Means so small deformation theory means your strains are small and there is a linear relationship between your strains and displacement. So strain displacement relationship is linear. So it is a small deformation theory and linear strain displacement relationship. Also, the relationship between stress and strain is also linear. So it is a linear elastic material. So that's why your stresses will be linearly dependent on your displacements because strains are linearly dependent on displacements and stresses are linearly dependent on strains. So that's why stresses will be linearly dependent on displacements. Anyway, so let me write there was a twist and then there is a term which is known as rotation. So this omega which I have written here, it is rotation. So let me just write rotation of cross section at any z. So that is denoted by rotation is denoted by alpha and this is a function of z. So this is given by twist times. So this is twist. So twist is per unit length and then rotation is at a particular length. So starting from let's say beginning of the shaft. Let's say you are at a particular x value, x is equal to small l, let's say. So I mean we are not denoting here, we are not denoting x's with variable x, rather we are using variable z for the x's. So let's say we are at length z is equal to small l. So alpha will be this twist times z. Okay. And let me draw the coordinate system. So this is the coordinate system. Again, I'm repeating if you want to go into the depth of these formulas, want to see the derivation of these formulas, please refer lectures again. So, so axis of the rod or shaft or cylinder is along z direction. Okay, and x and y is perpendicular to z. Anyway, but we will not deal in XYZ coordinate system. Rather, we will deal in R theta Z coordinate system. That is curvilinear coordinate system. Because whenever we have something circular, spherical, or any curvilinear curved body, so curvilinear coordinate system makes our job very easy. That's why we use curvilinear coordinate systems for curved bodies, and we go for Cartesian coordinate system in case our bodies are straight. We can use Cartesian coordinate system for curved bodies as well, but then it will complicate our analysis. Why it will complicate? You can imagine like this that in curvilinear coordinate system, the axis is aligned along the body. Let's say in a cylinder, theta coordinate is aligned along the circumference of the cylinder, right? R is aligned along radius of the cylinder. Z is aligned along axis of the cylinder. So the axis is aligned along the coordinate system is aligned along the body. So whenever you define coordinate, so let's say you want to move along the circumference of the cylinder, so you only need to increase your theta coordinate. But if you will deal in XYZ coordinate system, so if you will move along, let's say at a particular position or at particular Z, if you will move along the circumference, your X and Y both will change. But here, in case of curvilinear coordinate system, let's say you are moving around the circumference, so only at a particular radius, particular cross-section, so only your theta is changing. So here, that's why since your curvilinear coordinates are aligned along the surface of the body or along the geometry of the body, so it makes your job very easy. Okay, so let me go to the next equation. And in the previous week, we had learned about equilibrium equations in curvilinear coordinate system. Now the equilibrium equations in curvilinear coordinate system have been reduced for this particular cylinder case, for the case of this extension, torsion, and inflation of cylinder. Okay, and detailed derivation is given in lectures. I'm just writing the formula here. So the equation of reduced equilibrium equations in terms of stresses will be given by. So let me just write equation for equilibrium equation for extension, torsion, and inflation. Let me just write it down. And inflation of stress. So that is given by this formula here. That is del of sigma RR by del R plus sigma RR minus sigma theta theta over R plus body force in radial direction BR is equal to rho AR. AR is the acceleration in radial direction. So this is equilibrium equation in radial direction. So and all the differentials with respect to theta will be gone because in axisymmetric problem, displacement field will be independent of theta. So strains will be independent of theta. So that's why stresses will also be independent of theta. So all the differentiations with respect to theta will be zero. And so that's why in theta coordinate system we have b theta is equal to rho a theta only. All the differentials will go to zero. And in z you have del sigma z over del z plus Vz is equal to rho Az. So this is your equation for extension, torsion, and inflation of cylinder. That is axisymmetric problem. Now this is also valid for dynamic case. If you go for static case and let's say there is no body force present or no gravity is present. So no gravity is present, so there will not be any body force here. So we can say that if we say that for static and zero gravity problem, the above equation may be So it will be given by, tell me. So you just have to substitute Br equal to 0 because body forces Br, B theta, Bz will be 0. There are no body forces. And all the acceleration will also be 0 because it is a static problem. So AR, A theta, Az will also be 0. So you will be left with the first equation. You have del sigma RR over del R plus sigma RR minus sigma theta theta by R is equal to 0. And second equation will be 0 equal to 0. I'm not writing that. Third will be del sigma ZZ by del Z is equal to 0. Right? So this is your equation of equilibrium equation for acceleration problem for torsion, extension, torsion, inflation of cylinder, right? And in absence of any gravity or body force, and for static case. Okay, it's not for dynamic case. So in the lectures, the expression for sigma RR and sigma theta theta have been derived. So let me just write those expressions. Expression for sigma RR and sigma theta theta. These have been derived in the lectures. I'm just writing the formula. So those will be sigma RR will be given by, if you remember, it is A by 2 plus B by R squared. And sigma theta will be given by A by 2 minus B by R squared. And if you remember, sigma RR plus sigma theta theta, that was equal to A. And then sir has run the derivation to find out the value of A and B. So if you find out the value of A and B for thick cylinders, so we can say that thick cylinders, your A is given by 2p small r1 square over r2 square minus r1 square. So r2 is outer radius of the, it is a thick hollow cylinder actually. So r2 is the outer radius, r1 is the inner radius. So it is r2 square minus r1 square. And your B is given by, P is the internal pressure. So your B will be negative. So it will be minus of P times r1 square r2 square over r2 square minus of r1 square. And these are the values of capital A and capital B for thick cylinders. And then you have a torsion formula. So let me just write. So T is equal to Gj and omega by L. This omega by L was twist, right? And this is torque. This is torque applied to the cylinder. And this is the twist developed in the cylinder. And this is something known as torsional stiffness, right? Torsional stiffness of the cylinder. So it means you can write omega as TL over Gg. So this omega is nothing but end-to-end rotation. You start from one end and you go up to capital L. Okay, so that is end-to-end rotation. How much rotation of the cross section has happened when you start from z is equal to 0 to z is equal to capital N. So let me just write down the problems. So problem 1. So let me firstly write it down. Then I'll give you some time to solve this problem. Then I myself will do the solution of this problem and you can verify whether you have done it correctly or not. So let me just write. Suppose a solid disk of radius capital R and the hollow cylinder or hollow disk, sorry, and a hollow disk of inner radius capital R prime and outer radius capital R square. Okay, so these are shrunk fit together. So you would have studied about limits and fits. So these two solid disk and a hollow disk are shrunk fit. So for these two bodies to get shrunk fitted, what is the condition? So condition is that hollow disk inner radius should be a bit smaller compared to solid disk radius. So we can say that solid disk radius should be smaller, should be greater compared to this hollow disk inner radius. Only then they can be shrunk fit. So this is the condition. Further, assume that no external pressure is applied to the hollow disk. There is no external pressure is applied on the hollow disk. On the hollow disk, okay. And so these are some boundary conditions. So no external pressure has been applied on the hollow disk, and there are no axial displacements. So we say and that no axial displacement is allowed in the two disk. It means there is no axial strain that will be allowed in the two disk. There will not be any axial strain even due to Poisson effect. So when you will use shrunk fitting, obviously the axial displacement should have increased, but it is not allowed to increase. Okay, even due to Poisson effect. So no axial displacement is allowed. And you have to assume that let the two disks be made of same material. So what we can conclude from here is that only radial displacement which is denoted by UR, generates in this case. So only radial displacement is there. Okay. So now you have to, so have you understood the problem? So you have a solid disk of radius capital R and a hollow disk of inner radius small r and capital and outer radius capital R square. There is no external pressure applied on this hollow disk, and these two solid and hollow disks are shrunk fit. So if you want them to be shrunk fitted, so outer radius of solid disk should be greater compared to inner radius of hollow disk, that is R should be greater than R prime. And there's no axial displacement allowed in the two disks, and two disks are made of same material. So only displacement that will be left with will be radial displacement. So only radial displacement will be generated in this case. Okay. I mean, it is given in the question that only radial displacement will be generated. Now what you need to find out. So let me write it down as well. In part A, you have to write down all the boundary conditions. Or interface conditions required to obtain variation in radial stress which is sigma RR in the two disk. Firstly, you have to state all the boundary conditions and interface conditions to obtain variation in radial stress sigma RR in the two disk. Second part, you have to solve the governing equation. In the first part, you have to define boundary conditions. Second part, you have to solve the governing differential equations or governing equilibrium equations. I'm just writing governing equations here. So solve the governing equations and obtain expression for sigma RR in the two disk. Once you have the expression, you have to obtain expression for circumferential or hoop stress. So we should obtain expression for okay. So you have to obtain expression for circumferential and hoop stress or hoop stress as well. Circumferential and hoop stress are same. So can you give this question an attempt? Yes, please try. Firstly, draw the diagram and imagine that these two bodies are shrunk fit together. And then after that, you start writing the expression for, since only UR is present, so write the expression for UR. So in the lectures, UR was derived in terms of C and D, right? So firstly, you write the expression for UR in first body, UR in second body. C and D obviously will be different for two bodies. and then you write the expression for sigma rr. So there also the constants will be a and b, but this will be different for the two bodies. So there will be two expression for ur, one for body one for body two, and two expression for sigma r, one for body one for body two. So there will be total 16, sorry, 8 constants. 8 because when you write ur1 for first body, so there will be c1 d1 for two set of constants. Then you write ur2 for second body, there will be c2 d2 to another set of constants, which makes it 4. Then similarly you write two more expressions for sigma r, which will involve 4 more constants. So 4 plus 4 will be 8. Then there will be 8 constants. So you need at least 8 equations for solving these 8 constants. So how will you do that? So how many conditions are given to you? So um, let me just, so it is given to you that there is no axial displacement. So since axial displacement will not be there, so your longitudinal strain epsilon will be 0, or axial strain epsilon will be 0, right? So one condition you can use that, and then you can use interface condition. So interface condition will be the, so you can see that the increase in, so the decrease, so what will happen actually? So um, yeah, so the decrease in radius of this solid disk will be equal to increase in inner radius of the hollow cylinder. Okay, because at the interface, after getting them shunt fitted, so both of them will match actually. So both of the interfaces in both the bodies will be shunt fitted. So in the upper body there will be expansion of the radius, in the lower body there will be compression. So the reduction in of radius in the lower body will be equal to uh, expansion in the upper body. Okay. So one condition is that. So these are combined together. These are two conditions, but we need 8 conditions. So, and then at the interface, your sigma RR will be continuous. Sigma RR from body 1 will be equal to sigma RR from body 2. Why it will be continuous? Because when you see your differential equation, so um, it involves derivative of sigma RR. So this is just one view. So it involves derivative of sigma RR with respect to R. So del epsilon, del sigma RR by del R. So it means sigma RR has to be continuous with R. Okay, only then the differential will exist in the equilibrium equation. So sigma RR, that's why both from both the bodies should be same. Also, you can uh, imagine that sigma RR cannot be discontinuous in this case, because here, if even if you apply equilibrium, yeah, again you'll have to apply equilibrium equations. So if you draw free body diagram, so action and reaction on both the bodies will be same because it is a static problem. So this will lead to same sigma R at the interface. So that is third condition. And then at the outer surface, there is no pressure applied. That is fourth condition. Sigma R at the outer surface will be 0 because there is no pressure. So that is fourth condition. And then you have more conditions. Let me just see. Okay, at the center of the solid disk, your your displacement, because center of the solid disk will not involve any radial displacement because it is, I mean, it will not get compressed or extended. Center of the solid disk will experience, firstly, it will experience some finite sigma r, some finite stress will be there, and it will experience zero displacement. UR will be 0. So these are 6 conditions. Now you need 2 more. So can we get There are eight constants. Let me just write down, then we will see. Okay, you can just try. So these are six conditions, and you have eight constants. So other constants can be found out using. Okay, so when you will put this longitudinal strain will be equal to 0. So um, that you can put in both the bodies, in body 1 and body 2. So there will not be any longitudinal or axial strain in body 1 and body 2. So this will lead to two equations. I was counting them as one. So now we have seven equations, and one more equation will be required. So that we will obtain. Let me just see. So we have seven equations as of now. Now one more equation is required. So that equation I think will be equilibrium equation itself. Okay. So because we also have equilibrium equation, so that equation will be equilibrium equation. Okay. So this makes eight equations in total. I'll not be using equilibrium equation. I'll just directly be using the expression for UR and sigma R. So um, and those are derived based on equilibrium equations only. Okay, so equilibrium equation is not required. Still, in the expression of sigma R and UR, there are eight constants. Let me see. One more condition will be required. Can you tell me how we will get one more condition? Let me just write it down. The conditions, then we will see. This is the solution. So let me just draw the diagram first. I think let's say this is firstly I'm naming these terms. So let's say solid disk is body 1 and hollow disk is body 2. Okay. Now I'm just drawing this solid disk. Let's say this is a solid disk. So it has a radius, which is so this radius is capital R. Okay. Now you have a hollow disk also. So the radius will be somewhat smaller than capital R. So this is hollow disk, and let's say it has inner radius R prime, and its outer radius is capital R square. Let's say this is its outer radius, and it is given by capital R square. Okay. And here we know that capital R is greater than R prime. So what kind of forces that will be there? So in the solid disk, at least, in the solid disk, what kind of forces will be there? So there will be compressive forces because it is being strung fitted into this hollow disk, and I mean this is solid area. and this is completely solid. So it is strength fitted in this hollow disk. So it will apply this disk will try to compress this one because capital R is greater than R dash. So there will be compressive force. On this solid disk, right? And similarly, here internally on its internal radius, there will be tensile force. So force will be tensile here. And there will be some pressure. Okay. Now, let's say initially it has radius capital R, the solid disk. And so this is body one and this is body two. Initially it has a radius capital R. Now after deformation, let's say radius is R plus, let's say we have a radial displacement UR here. UR 1, I'm saying, because it is corresponding to this hollow disk. So radial displacement of hollow disk at 1 at radius R. So it is not multiplication, but I'm just saying that this UR is a function of R. Okay, capital R. Similarly, here, if I see here this radius, let me use some different color. Screen. So here this radius. This will be initially it was R prime, then it will have some displacement. Let's say the displacement is UR2, and which is a function of R prime. Okay. I mean, it is a function of radius. That's what I'm saying. This will be the displacement of this radial displacement of this circumference, or at any point on this circumference. And there is one more condition that here there is no pressure. So we say that here there is no traction on the outer surface of this solid hollow disk. And let's say here we have sigma RR. So there will be radial stress also. Let's say this is sigma RR1 corresponding to this body, and then here also we'll have radial stress. So this is given by sigma RR2. Obviously, these two will be equal as we have discussed because commutativity of radial stress will be there from equilibrium equations. So let me just write down a few more things. Let me just tell you about shrink fit. So shrink fit is usually performed by heat treatment. Okay, and that is by heating the hollow disk. So firstly, this hollow disk will be heated and its radius will get expanded. Now this solid disk, which is at room temperature, will be inserted in this hollow disk. Now since its radius has been expanded due to heating, it will get inserted here easily. Now this hollow disk will be allowed to cool down. So then its radius will decrease and then they will both get shrunk. Let me just write it down. What I've said right now. So we can say that shrink fit is usually performed by heat treatment. That is by heating the hollow disk, or we can say that it will expand the disk and its radius. It will expand the radius of the hollow disk and then fitting this hollow disk over the solid disk, fitting over the solid disk. and then allowing to pull it and then pulling it down. So, right? And then what will happen? So solid disk and hollow disk. So I've already written that. Let me just write it down. Solid disk and hollow disk are represented by superscript 1 and 2 respectively. So you know the formula of radial stress. So we can say that finally what you need to find out is you need to find out expression of sigma RR in the two disk, right? And then you have to find out expression for sigma theta theta also at the end. So we can say that radial stress, once we know sigma RR, we can find out sigma theta theta because sigma RR plus sigma theta theta is equal to A. So their summation is constant. So once you find sigma RR, you can easily find out sigma theta theta. So let me just so radial stress will be given by, remember the formula sigma RR will be again a function of R, and for the body one I'm writing. So that will be A by 2 plus B by R square. And since it is corresponding to body one, so that will be 1 and A1 and B1. Similarly for body 2, that is the hollow disk, will be a function of radius, and that will be given by A2 by 2 plus B2 by R square, right? And if we write the radial displacement, so radial displacement will be given by UR for body 1, which will be a function of again radius, and that will be CR by 2. So expression is ER by 2 plus D by R, right? So this was the expression for radial displacement. And since it is for body 1, so it will be C1 and D1. Similarly for body 2, this will be UR2, and which will be a function of radius. And this will be again C2R by 2 plus D2 by R. Okay. So now we have 1, 2, 3, 4, 5, 6, 7, 7, 8. 8 constants A1, B1, A2, B2, C1, D1, C2, D2. Right. So now I'll try to reduce equations. So I will say that as axial strain is given to be 0, axial strain epsilon is 0. So what will happen because of this? As axial strain is 0, so if you recall the lectures, this A was given in terms of C and epsilon. So since epsilon is 0, so A will be equal to 2 into lambda plus mu times C. And then there was an expression for B also. So B was given in terms of D, so that was 2 mu D. So from the lectures, you can derive a relationship between A and C and B and D. And how you can derive is you have sigma r and sigma theta theta in terms of A and B, and you are in terms of C and D. So, and you have equilibrium equations also, which is in terms of stresses, but you can convert them in terms of displacements. You are okay. So using these three equations, you will be able to derive the relationship between. So there will be relationship between A and C, and there will be relationship between B and D. So obviously here C is there, and plus some epsilon term was there, epsilon and something. Since epsilon is zero, so this term will go away. So only this expression will be there. Okay. And since this expression is valid for, so axial, since axial displacement is valid for, I mean axial displacement is zero in both the bodies. So this expression is valid for both the bodies. So that's why here I'm writing I, AI and CI, and BI and DI means A1 will be related to C1 and A2 will be related to C2, and B1 will be related to D1 and B2 will be related to D2. Okay. So here, how many equations we will have? So from this, we will get two equations. From here also, we'll get two equations. So in total, we will have two equations. I mean, four equations. So it means A1 will be equal to 2 times lambda plus mu and C1. And you can say A2 is equal to 2 times lambda plus mu times C2. And here you have B1 is equal to 2 mu D1. And you have B2 is equal to 2 mu D2. We have four set of equations here. Now I'm using other boundary conditions. So again, part A I have written. So you have to, in the part A, you have to write all the you have to write down all the boundary conditions and interface conditions required to obtain variation in radial stress. So I have not completed this part. Actually, this part A is going on from here. So let me write down the boundary conditions also. So this was the use of uh, axial strain equal to zero, axial displacement equal to zero will lead to axial strain equal to zero. So it leads to four equations. Okay. Initially we were considering I think only one, so that was a mistake. I mean, obviously when you will write down the things only then you will get to know how many equations will be there. So let me write boundary conditions. Boundary conditions. First boundary condition is radial stress will be continuous. So sigma RR for first body at radius R should be equal to sigma RR for second body at radius R prime, right? Because, and we are taking reference configuration as the undeformed configuration. So initially when the bodies were undeformed, so that is the reference configuration. So obviously after deformation R plus UR1 will be equal to R prime plus UR2. So because both the radius of inner outer radius, I mean radius of disk will be equal to inner radius of the hollow disk. So radius of solid disk will be equal to inner radius of the hollow disk after deformation. But we are considering reference configuration to be undeformed configuration. So anyway, so this is sigma RR at the interface will be equal. So that is one condition. So we can say that this is continuity of radial stress. And this comes from equilibrium equations. Because in equilibrium equation you have del sigma RR over del R. So that will be like this only if your sigma is continuous is required. So differential only exists when your function is continuous. Okay, so and also if you forget everything, all the equilibrium equation, I mean this partial differential equation, if you try to draw a free body diagram also, so from the free body diagram Also you will get that you will get to see that the radial stress at the interface for both the bodies will be equal because the reaction at the interface will be equal. Only then it can be in static equilibrium. Okay. So you can say that this is radial stress at the interface. This also. Both are radial stresses at the interface. And then we have second equation where you have after deformation radius of solid disk will be r plus ur1, which is a function of radius. So this is at radius equal to r, and then you have r prime plus ur2, and ur is a function of radius, and we are finding it at r prime. Okay, so these two will be equal because after deformation, the radius of solid disk will be equal to radius of inner radius of the hollow disk. Now the third condition. Third condition will be sigma rr traction at the outer surface is 0, sigma rr in second body at radius r square at the outer radius, so that is 0, right? So r square, or because outer radius is r square, so I'm just writing. You can write r2 also. R2 will, if it gives you clarity about outer radius. So if you want to represent outer radius with r2, so let's say this is r2, so that is 0. It means that your r2 is capital R square. So the second body, there is no traction. That's why this will be 0. So this boundary condition, this boundary condition is the shrink fit condition. And the third boundary condition is traction free boundary condition. Okay. And the fourth boundary condition you have, fourth is um, we want that sigma rr in first body at r is equal to 0. Yes, it should be some finite value, right? Because it will be some compressive stress in this problem. So radial stress at the center. And it is also clear that radial displacement at the center of the first body, that is solid disk, will be 0. Because center is not going anywhere. Okay, so obviously it is at r equal to 0. Okay. Now let's solve this. So this first part we have done. We have written all the boundary condition and interface condition. Now you have to solve the governing equation and obtain expression for sigma r into disk. So if you solve this, so let me just go to part B. Let me tell you how to solve this. So let me write down the expression for sigma rr1. Sigma rr1. So that was given by, that is a function of obviously radius r. That was given by so I'm just inserting the value of a1 and b1 here. So a1 b1 from here. So here you know that yeah. So a1 is 2 into lambda plus mu into c1. So I'm using these values, and a2 is 2 into lambda plus mu into c2, and b1 is 2 mu d1, and b2 is 2 mu 2 mu d2. So I will not write a1 a2 b1 b2. Rather I will write c1 c2 and d1 d2, because a and b also you can express in terms of c and d. So I'm just writing here. So sigma rr1. So it was a by 2 plus b by r square. So instead of a, I'll use c. Instead of b, I'll use d. So let me just write. So this will be lambda plus mu times c1, and you have at the place of b by r square, you have minus 2 mu d1 by r square, right? Yes, very fine. Yeah. So this was a by 2, so that's why it is lambda plus mu into c. And similarly, in the second body, it will be given by lambda plus mu times c2 plus, I mean, minus, it will be minus because b is minus 2 mu d2 over r square. Okay. Now, from this condition, the fourth condition, that in sigma rr1 has to be finite at r is equal to 0. So if you put r is equal to 0 here, so this is in the denominator, so it will become infinite. This term will become infinite. So it is not satisfying this condition. So for this conditions, if we have to satisfy this condition, so d1 has to be 0. So this whole term will get 0, will be 0, and there will not be any contribution of r in the denominator. So from here we can conclude that this d1 will be 0. This will be 0. And then, so let me just write it what I have done. So what you have to do is you have to apply boundary condition. Which boundary condition you have applied? You have applied that sigma rr1 at r is equal to 0. That will be 0. And this leads to d1 equal to 0, right? This leads to this. So we have found out one constant now. And let's use another boundary condition, which is sigma rr at 1 at r is equal to capital R. And I'm using this boundary condition, the third one. And this should be equal to, oh, no, the third one. Sorry, the first one, that the radial stress at the interface should be equal. Okay. So radial stress corresponding to both the bodies at the interface should be equal. So sigma rr at 1 should be equal to sigma rr at 2 at r prime, right? So if you do that, what you will get? Let me just put the values. So put in this equation and this equation. Put them equal. So if you do that, so it will be lambda plus mu. It is independent. So sigma rr is independent of r because you have only lambda plus mu times c1. So that should be equal to lambda plus mu times c2 because this d1 is 0. I'm not writing this down. Okay. That should be equal to lambda plus mu times c2 minus 2 mu d2, and this should be equal to r prime square, right? Because r is equal to r prime. This is fine. So let's say this is equation 1. Now only constants that we need to find out are c2, c1, c2, and d1, right? Sorry, c1, c2, and d2. These three constants we need to find out. We already have d1, right? Which is equal to 0. Once we have the value of all these three also, c1, c2, d2, we already have d1. So we can find a1, b1, a2, b2 also, because a1, b1, a2, b2 are in terms of c1, c2, and d1, d2. Okay. So right now we have used this condition, and we have used this condition also. Let me use different color, yellow color. So we have used this condition, and we have used this condition number 1. Okay. Now we will use condition number 2. So if we do that, so this condition, if we use condition number 2, so let's say we have used this also. So if you do that, so we will get u at u1 in body 1 at r is equal to r plus r. So u1 in body 2, I mean u in body 2 at r is equal to r prime plus r prime. These two should be equal. So we have the expression for u, which is cr by 2 minus um, cr by 2 plus d by r. That is the expression. So because in body 1 we have d1 equal to 0, so I'm just writing here c1 r by 2, and d1 is 0. I'm not writing here, so it is plus r. Okay, and this should be equal to mu2, which is c2 r prime by 2 plus, it is minus actually. The expression is, let's see, um, it's plus. Okay, so this will be plus d2 by r. Right. So let me just rearrange this equation. So let me bring c1, c2 this side. Anyway, you can just name it as equation number 2. Okay. And then let's use this equation, third one, which is sigma rr at in the second body at r is equal to r2 will be 0. So sigma rr you already know. In the second body, this is the expression for that. And r2 is r square, so I just need to put r square in this expression. So you'll get lambda plus mu, right, c2 minus 2 mu d2 divided by r square to the whole square, because r is r square, and this should be 0. And this is equation number 3. So now you have three constants, three unknowns, c1, c2, and d2, and three equations, 1, 2, and 3. So you can solve for c1, c2, and d2, right? And there is one more condition that is left, which is ur at ur1 at r equal to 0 should be 0. So let me just see. So actually these two conditions are very similar, because if you see here from this condition, what we have obtained, that d1 is 0. Okay. If you put d1 0 in the expression of ur1, so ur1 is this one. If you put d1 0, if you want at r is equal to 0, u should be 0. But if r will be in denominator, it will go infinity. So that's why this also implies d1 equal to 0. So if you put d1 equal to 0 at r is equal to 0, ur1 will itself be 0. So these two conditions are interrelated actually. These are not independent. That's why I have written in the same line. This also we have used. Okay. So now we have used all the conditions. So actually we had four boundary conditions. I mean, and this one condition, which is angular displacement equal to 0. This led to four equations, and these four boundary conditions led to another four equations. So total like 8 equations are there, and there are eight unknowns. A1, A1 B1, A2 B2, C1 D1, C2 D2. So that's how we have found out. Now at the end you have three equations and three unknowns, that is C1, C2, and D2. So you can find it out easily. And once you will find it out, you can put in the expression of sigma rr. Once you have sigma rr, you can get sigma theta theta, because summation of both of them is um, a. Okay. So let me just write it down what I have said. So you can say that solving equation 1, 2, and 3, we can obtain C1, C2, and D2. Then finally, put these values in the radial stress expression. Right. So once you have the radial stress, you can find out the circumferential stress also. So circumferential stress or hoop stress, the expression for that is we have written here. That is also dependent on A. So that is A by 2 minus B by R square. So once you have A and B, you can write the expression for sigma theta for both the bodies. So let me just write it down. So once the value of constants are known, we get sigma theta in body 1, which is a function of R. That will be lambda plus mu times C1, and sigma theta in body 2, which is also a function of R. Because A1 was lambda plus mu times C1, and A2 was lambda plus mu times, I mean twice of that. So here it was A by 2. And here it is minus B. So B is minus 2 mu D. So minus minus will be plus. So this will be plus 2 mu D2 by R square. Right. So this is the expression for sigma theta. Okay. So body. Okay. So we can, so you just have to find the value of C1, C2, and D2. Okay, let me go to the next question. So problem 2. In problem 2, you have to derive the expressions for sigma RR, sigma theta, and sigma ZZ for thin pressurized tubes. With application to pressure vessels. Okay, so I just do this solution. Let me draw the cylinder. So this is a cylinder. So let's say this is a thin cylinder. Okay, and the thickness will be, let's say this is T, all thickness, and it is subjected to pressure. So this is the internal pressure that it has. And here also it will act, and here also it will act. And it is pressure P. And let's say it has outer radius as R2 and inner radius as R1. Let's say this is outer radius, which is this radius is given by R2, and its inner radius is um, let me see. Yeah, so it has some inner radius also. So Let's say that it's like this. This will be the inner radius. This is inner radius. R1. So, and obviously this is z coordinate. Z coordinate is taken along the axis of the tube. So we have the expression for thick pressure vessels, and we need to derive for thin vessels. So one assumption will be there that this R, let's say R1 or R2. So we will say that R1 by T will be very large because T is very small. Okay, and we will say that also R2 will be approximately equal to R1 because it is a thin pressure vessel. So since T will approach to 0, T is very small, so that's why this R2 will approach to R. Now you have, let me just write it down. So you have four thick pressure vessels. You have A is equal to 2P R1 square over R2 square minus R1 square. And you have sigma RR is equal to A by 2 plus B by R1 square, right? And B by R1 square at B by R square, rather I should write. And I mean, let's say I want to write it at radius R is equal to R1, so that will be radius stress at R is equal to R1 in the radius. And you have value of B is minus P times R1 square R2 square over R2 square minus R1 square. And sigma theta theta. So that is, let's say I want to write it at R is equal to R1, so that is A by 2 minus B by R1 square. I want to write it at R is equal to R1 only. Okay. So for thin cylinder, this is the expansion. This is the assumption that that will be valid. So if we apply this assumption in this formula, so for thin cylinders in pressure vessels, we have, let's find out the value of A. So A will be 2P. And one more thing is R2 minus R1 is equal to T, right? Here I should also write. Okay, so you have here 2P R1 square and R2 square minus R1 square can be written as R2 plus R1 and R2 minus R1. And R2 minus R1 is T and R2 is equal to R1. So we can say that it is 2P. So it is 2P R1 square over R1 is equal to R2. So this is 2R1 and R2 minus R1 is 2T. So this will be T. And sorry, R2 minus R1 will be T, not 2T. So finally you will be left with P R1 by T, right? This is the value of A and value of B. Try to find out. So that will be minus P times R1 square, R2 square. Again, you have R2 minus R1 square. So again, here you have R2 plus R1 and R2 minus R1. So this will lead to minus P R1 square, R2 square over. So this will be 2R1 and here you will have T, right? So finally, what will you get? You get minus P R1 R2 square. And obviously R1 is equal to R2. So we say that it is R1 cube, P R1 cube over 2T. Okay. So that's what we are getting. And if you put in the expression of sigma RR, so let me find out generalized expression for sigma RR. So sigma RR is A by 2 plus B by R1 square. Okay. R1 square means I want to find it at R is equal to R1. So that's why I've written R1 square can be any radius. So if you substitute the value of A and B now, so A will be P R1 by 2 and B is minus of P R1 cube over 2t, and here already there is R1 squares. So finally, what you will get? So this will be 0, right? So no radial stress. So actually, it will be very small compared to other stresses. That's why it's coming to be 0. Now let's find out sigma theta theta. If we try to find out sigma theta theta, so that will be a by 2 minus b by r1 square at inner radius. So that will be, if you do that, so this will be p r1 by 2. Here will be t, obviously. T minus b again p r1 cube. This will be plus because b is already minus. So this will be PR1 by 2t plus PR1 by 2t. So this will be PR1 by t. So there is a circumferential stress or hoop stress. And this will be assumed as constant only because see here, because R1 is approximately equal to R2, so it's almost equal across the radius. Okay. And sigma ZZ also we need to find. So we say that sigma ZZ does not vary through the wall thickness. And this was an assumption that was initially taken. It's not an assumption of thin cylinders. It is valid for thick also, because if sigma ZZ varies uh, with thick wall thickness or radius, the warping of the cross section will happen. So we don't want that. Anyway, so sigma ZZ does not vary. Oh, sorry, that was related to UZ. Okay, so if UZ will vary with radius, so there will be warping of the cross section. Since UZ is not varying with radius, so epsilon Z will also not vary with radius, and sigma ZZ so that it does not vary with wall thickness. Let me see. Mm, yeah, yeah, so it will not vary. So because we do not want warping of the cross section, the sigma ZZ does not vary through the wall thickness, and accordingly, and there is no external force acting on this cylinder, only there is internal pressure. There is no external longitudinal force that is there. So, and accordingly, when no external force acts on the cylinder, so when no external force is acting, and what do we have? We have sigma ZZ, it's already been derived for thick cylinders, so that was pi r1 square p over um, divided by radius. So p into pi r1 square is the net axial force that will be acting on the cylinder due to pressure divided by area. So area is pi times r2 square minus r1 square for thick cylinders, thick monocylinders. Okay. So, and if we do it for um, thin cylinders, so since, let me see what we'll get. So this will be R2 plus R1, and this will be R2 minus R1. So R2 plus R1 is again 2R1, right? And this is T. So you will get PR1 by 2T. So you get PR on by 2. Finally, you will get sigma z, that's PR on by 2. So this is the approach where we have used formula of thick cylinders and then we have arrived at the formula of thin cylinders. There is a direct approach also using force balance. So let me use that. So second approach, that is using force balance. So firstly, let me balance the force along z direction. The force balance along the z direction. Let me draw the cylinder. Cylinder will be same. So, but let me just. Okay. This is the cylinder, and this is the thickness of the cylinder. This is the, let's say this is R1, and this will be outer radius. Here, this will be R2, and there will be internal pressure, which is P. So this is internal pressure. Now, and this is obviously z direction. So something. Sorry, pressure will act here also. Now, if you balance the force in z direction, so what will happen in z direction? We will have this cross section, right? And we will have this kind of saying. I'm just drawing the front view of the cylinder. So this is the cylinder you are looking from here. So this is the front view. So and let's say this is, and z direction pressure will be acting like this here and upward obviously and below. So above and below pressure will be balanced, only unbalanced, and here there will be stresses sigma zz. So that will sigma zz will develop in the cross section of the thin cylinder. So this is sigma zz, which is uniform. So let me apply the force balance. So how will you do that? If you apply the force balance, so sigma zz multiplied by the this cross section. So this cross section is nothing but 2 pi r times thickness. 2 pi r1, let's say, times thickness. So that is the area of this cross section of thin cylinder. And this is now the resistive force provided by the stresses, internal stresses, and this should be equal to the external force, which is pressure times area of the cylinder, which is pi r1 square, right? So this force is applied here. This is the external force due to pressure, and this is the internal resistive force. So these two should be equal. Now, if we find out, so what will you get? Sigma zz from force balance. So you will get P times R1 by 2T. And this is the same expression that we were getting here, right? So you can do easy force balance. You cannot do it very easily in case of thick cylinders because in thick cylinders, the sigma RR and sigma theta, sigma RR will be a function of radius and sigma theta will also be a function of radius. So if you want to find a total force due to this total resistive force, you need to integrate across. You cannot write directly. You need to integrate across the radius to find out the total force because sigma RR will be varying with R. Anyway, but here since these are constants, sigma RR, sigma theta are constants, not varying with radius. So you can directly write. You can directly balance the force. Now let me do for sigma theta theta. So for that, if this is the cylinder, let me cut the cylinder from the center and look it from the bottom. So if I do that, so the cylinder will look something like this. Oh, sorry. Okay. And we have this. This is the cylinder. So and here also it will be seen. This will be the pressure that will be acting. Okay. And let's say this is the radius R1. R1, R2 will be same numbers. And on this cross section, let's say this is the internal resistance in the downward direction that will be provided. So on this cross section, so this is a flat cross section. Now on this cross section, the internal resistance will be acting, and that will be provided by sigma theta theta or hoop stress. Right? And obviously sigma RR will be zero here because out at outer radius there is no traction. Sigma RR will be zero at the outer radius. And here also there will be sigma theta theta. So sigma theta theta will cover how much area. So net force that will be resisted by sigma theta theta will be sigma theta theta times this cross section area, which is length times thickness. And there are two such um, strips. Okay, so this will be 2 times length of cylinder times thickness, right? And this should be equal to the this should balance this pressure force. So this pressure force, if projected on a flat surface, so let's say it's on this surface, so net force that will be acting will be pressure times this total, that the area or the center of the cylinder. So this will be P times center of the cylinder has a radius of 2r1 and length as L. So this will be the net force balance. So sigma theta theta will be equal to, now 2 and 2 will get cancelled. L and L. So you get P R1 by 2T. P R1 by T, because 2 and 2 will also get cancelled. This was the same thing that you are getting from by reducing the formula of thick cylinder to thin cylinder. So this is the same thing that you are getting. Now sigma, let's talk about sigma RR. So I'm just writing down sigma RR will be 0. Why it will be 0? Because internally at a point, at this point it will be equal to minus P, and at outer surface it will be 0. It will be minus P because here traction is minus P only. Compressive pressure force is acting. It will compress the radius. I mean this thickness part, it will compress from here. So sigma R will be minus P here at the inner radius, and outer radius it will be 0. And it is varying from minus P to 0 within a very small thickness. And these terms, sigma theta theta and sigma z z, these are very much greater than P, because this R1 by T ratio is um, very large compared to 1. So that's why these terms are very much larger compared to P. So that's why this will be larger compared to sigma RR also. That's why sigma RR has been taken as 0. So let me just write it down. So, so when we consider outer traction So when we consider outer traction, outer traction free surface, because outer surface is traction free here. So when we consider outer traction free surface, that is sigma rr is equal to 0, and the internally pressurized surface, it means your sigma rr may be equal to minus p. Okay, so we say that sigma rr varies from minus p at the inner surface to 0 at outer surface. And we know that r1 by t is very much greater than 1. Okay, so this implies we can say that p r1 by t and p r1 by 2t for hoop and circumferential stress. Sorry, for hoop and axial stress, not circumferential. Axial stress, respectively, will be very large compared to p. Since this is very large compared to p, we can say that therefore sigma rr is neglected and set to 0. Let me go to problem 3. So problem 3 is two shafts AB and BC of equal length and diameter d. They have equal length and equal diameter. I mean, diameter are not equal, diameter are d and 2d. They have equal length only. These are made of same material. And they are joined at B through a shaft coupling. While the end while the ends A and C are built in. Built in means they are clamped, you can say. Further, a twisting moment and the magnitude of twisting moment is capital T is applied to the coupling. If TA and TC represent the twisting moment, so TA and TC are twisting moment in A and C. I mean at so that will be experienced at A and at C. Find the relation between TA and TC. So two shafts AB and BC of equal length and diameter. So diameter have equal length and diameter as D and 2D are joined through a shaft coupling, and they are applied with some torque. Coupling is twisted with some torque T. So, so at point A there will be uh, twisting moment TA, and point C there will be twisting moment TC, and you have to find relationship between T and TC. So when you are twisting two shafts using a coupling, so at the point where the two shafts are connected through a coupling, so the coupling shaft A and shaft AB and shaft BC and the coupling, all three have the same twist at that point. So we will use this condition. All three have the same rotation, you can see. So all three will have the same rotation. So we will use these condition to find out the relationship between T and TC. So let me just draw the diagram first. So diagram will be something like this. So this is a, let's say, smaller shaft with smaller diameter. And then this is a shaft with bigger diameter. And now they are clamped. Here they are clamped, is clamped. Here it is clamped. In between they are connected through some coupling. Let's say this is the coupling to which they have been connected. Okay. And they both have the same length. Let's say that they have this length as L, and this length is also L. And we know that this is 2D and this is 2. So let me just write down what I have said. So here the rotation on both the shafts will be same. Will be same at B. Obviously, this is point A, B, and BC. Since rotation is same, you know that formula for T was um, GJ and omega by L, right? So the formula for omega will be TL by GJ. So since it's same for both the shafts, so we say that omega AB will be equal to omega BC. So let's say the twisting moment at A is TA. So TA L is same. Yeah. In shaft 1, I'm just writing 1. So let's say T1 L1 by material is same. So G1, I'm just writing it G1 J1. So T2 L2 by G2 J2, right? So since T1 and T2 will be different, L is same. So this will be L and this will be G. Material is also same, and G1 and J. And these twisting moments will be, since we are taking capital L. So if we start from this point also, and we apply twisting moment here, so total rotation will be omega AB. And if we start from this point also, and if we apply twisting moment here, so total rotation will be omega BC. So that's what we are doing here. So T2L divided by J2. So L and G will get cancelled. So T1, which is at point A, and J1 is nothing but pi by 32 and d to the power 4. And this is polar moment of inertia, which is pi by 32 d to the power 4. And here, which this is Tc, and this is pi by 32. And now our d is 2d, so this is 2d to the power 4. This implies uh, Ta will be equal to Tc by 16, or Tc will be equal to 16 times d. Now, if you analyze this, what do you get? So twisting moment at C will be 16 times that of A. So here, twisting moment will be more. Why it is more? Because this is a small shaft, has smaller diameter. So that's why torsional stiffness will be smaller, because GJ represents torsional stiffness, right? So since torsional stiffness is smaller, so torque required for same rotation will be less. And here, torque required for same rotation will be very high, because here the torsional stiffness is high. Okay, let me go to problem 4. So problem 4 is a torque capital T is applied at the free end of a stepped rod of circular cross-section of circular cross-section. Okay. And this is as shown in figure. I'll draw a figure. The shear modulus of the material of the rod is G, capital G. The angular twist actually we should call it as rotation, because twist is something defined is omega by L, right? Yeah. So let me just call it as angular rotation, not twist. So angular rotation omega at the free end is, so firstly you have to find the options are given to you. A is 32 TL by pi g d to the power 4, and B is 18 TL by pi g d to the power 4. C is 16 TL by g to the power 4, and D is 2 TL by pi g to the d to the power 4. Now the diagram is for this question is like this. Okay. And you have this is length, and this is L by 2. Okay. And this is 2D. This is D. And this is, you can say, road 1. This is road 2. And yeah, that's it. And obviously torque is applied here. So you can say this is torque T. Twisting the values. Now yeah, please try to find out. You have to find angular rotation omega at the P end. So the end is fixed when you apply torque. Okay. So this torque you're applying here. And if you draw the free body diagram, from here it is fixed. So here you have applied a torque. If you draw a free body diagram and if you try to balance torque here at this point. So here also in this shaft, the torque that will be acting will be in anti-clockwise direction and the magnitude will be same. Only then there will be static equilibrium, right? Similarly, the torque that will be transferred into the bigger shaft will be T again. Okay. You can say that this torque is going to be same throughout the body. Okay. Whereas here the case was different because here the rotation was same. Okay. Here this end was experiencing the same rotation for this shaft also and this shaft also. That's why here TA and TC were different. But now also this was fixed. But here the problem is different. You have applied a torque and this end is free. So from the Fibonacci diagram, the torque will change. I mean torque will be same. So here also there will be same torque. Here there was torque was changing because you see here you have TC, here you have TA. And if you draw the free body diagram, so here also there will be TA, here also there will be TA. I mean, how it will vary. So TA is GJ omega by N. Okay. So omega is the total rotation, and is the it just depends on total rotation. So I think in this case, in this shaft there will be TA, and in this shaft there will be TC. But in these two shafts, the torque will be different, and there will be transition from TA to TC through this coupling. So in this coupling, there will be a variable torque. That's what I'm going to perceive. Anyway, so let me just see. Yeah, only then if there is some torque acting here and I draw the free body diagram, there will be same torque here as well. Same torque here, same torque here as well. So yeah, in the shaft, there will be some variable torque that will be acting. Okay. So torque will be going from TA to TC in this through this shaft. And since there is a variable torque, so what will happen if we apply varying torque which is varying across the length? So obviously then I think this linear relation will not hold true because here the torque is dependent on total rotation. So once this total rotation is fixed, um, anyway, so if this torque is varying across the length, so that also is a nice problem. We can try to solve that shaft subject to varying torque across the length. Let's say variation is linear. So you can substitute here, and this twisting can be a function of L, so linear function of L. So if we consider this to be Z, so this will be um, omega by L times Z. So that will be the angle that will be twisted. And this will be, I mean, it will be a nice problem. We can try to solve it, but these problems are not of such type. Anyway, so here in this problem, we have to find total angular twist. So if we try to draw the free body diagram, so in this small shaft, which is D, so diameter D. So since here there is a torque T, here also there will be some same torque T, just a moment that will be acting in the bigger shaft also. This twisting moment will get transferred. T, okay. This is obviously 2D. So if you try to find out the angular rotation, first you will find the angular rotation of this shaft, which is which will be angular rotation from the clamped end. So here angular rotation will be 0 and there will be varying angular rotation, and here there will be some angular rotation. So some angular rotation will be there, and then there will be some angular rotation of this shaft. But total angular rotation will be summation of angular rotation of this shaft plus this shaft, because once this cross section has rotated up to here, let's say, then the next angular rotation of this shaft will be an addition to that angular rotation. Because let's say this is the shaft and it has been angular and it has some angular rotation. Now one more shaft is connected. So it has almost rigidly rotated up to now. And now if we further rotate this shaft, so we are just applying superposition. Firstly, we are rotating this. So it has rotated up to some amount. And then we are keeping this as fixed, the white one, and the rotating the second one. So it will rotate. Um, rotation will be rotation of first shaft plus the rotation of this shaft if we apply some more torque to it. Okay? Because its cross section has already been rigidly rotated when we were twisting this white shaft. Then this my finger, which is representing a shaft, so it will be rigidly rotated first, and then the twisting moment will be applied. So it will have some more rotation. So let me just write. So angular twist omega, angular rotation at least. Angular rotation omega at the free end. So that will be omega will be equal to omega rho 1 plus omega rho 2. So that will be G1 L1 by G1 J1 for rho 1, and then it will be G2 L2 by G2 J2 for rho 2. Now T1 is T only, L1 is L, and G1 is G only because the material properties are same. And here you have J, which is pi by 32, and 2d to the power 4 plus 2 is to T, and L is L by 2 here, and G is same, and you have pi by 32 to the power 4, 2d to the power 4. Now if you take, what you can take common is, you can take 32 TL by pi d4G, so that you can take as common. If you take 32 TL by pi d4G common, so from the first part you will have uh, 1 over 16. It will be left from the second part, you will be have 1 over 2. So if you solve these two, we'll get 9 over 16. So it will be 32 GL over pi d4G times 9 over 16. 16 32. So we'll get finally 18 TL over pi d4G. Right? So option B is correct. So that's how you have to do these kind of problems, and you can try a problem with in which bar is subjected to variable twisting moment. So this twisting moment is very respect to L. Okay. So then maybe if I try to write that, so this T will be function of L, and actually you have to integrate. So yeah, this will not be a straightforward problem. You have to perform integration because T will be varying with L. So your omega will also, I mean, this is the total rotation of length L. If you take some another length, let's say small l, so rotation will be there. There will be not omega. I mean, you can represent it omega, then omega will be a function of small l. So omega, obviously, this omega also is the end rotation. It is a rotation at the end. But if you will take rotation at any cross section, so you can denote it by some other symbol. Okay. Okay, so we'll stop here for today, and we will meet in the next class. Thank you for your attention.